Welcome to the deep dive. We're here to help you get up to speed on the interesting stuff happening out there. We dig into the research, pull out the key bits, those aha moments.
Exactly. We do the legwork so you get the insight without the overwhelm.
And today, wow, we're diving into something really at the forefront of AI evaluation.
That's right. We're looking at a new benchmark called Bench. It's a fascinating way they're trying to figure out how generally smart these large language models, these LLMs, really are.
Okay, Geekbench. Sounds different. Not like the usual tests.
Not really, no. The
Yeah.
core idea is pretty novel. Instead of using existing tests or data, Bench actually gets the LLMs to, well, create the tests themselves.
Great. Create the test? How does that work?
It's a multi-step thing. First, an LLM comes up with the rules for a brand new game, like describes it in plain English.
Okay, game designer AI. Then what?
Then, the same LLM actually codes that game, turns a description into a playable environment using Python and a framework called Gym. Think of it like building the actual software for the game.
So it designs it and builds it.
Okay. And it doesn't stop there.
Yeah.
It then uses reinforcement learning RL to train another AI agent to become really good at playing this newly invented game, usually through self-play,
Yeah.
where the agent learns by playing against itself.
Right, self-play. Got it. So the LLM invents a game, codes it, trains an expert player, and then it comes the evaluation.
Exactly. That's the final step. They take other LLMs, the ones they want to test, and pit them against these trained RL agents.
Yeah.
The LLM gets the game description, sees the current state, the valid moves, and has to decide what to do.
And the key idea here is that this game is completely new, right? Something the test-taking LLM definitely hasn't seen in its training data.
Precisely. It's designed to test true generalization. And interestingly, the researchers found that the LLMs often create games that, well, even they struggle to play effectively against the trained agent.
That's kind of mind-blowing. So our mission for this deep dive is to really unpack Bench. We want to get a handle on how it works, why it matters, what it's telling us about where AI is right now.
And maybe what it hints at for the future, yeah. It raises some big questions about general intelligence.
Sounds like a plan. So maybe we should start with that bigger picture. The whole idea of general intelligence in AI.
Good idea. Because, that's been the dream for a long time.
Right, way back. The Dartmouth conference, wasn't it? Mid-50s? They had these huge ambitions.
Absolutely. People like John McCarthy believed, fundamentally, that we could eventually describe and simulate pretty much every aspect of human learning and intelligence in a machine.
But it didn't quite pan out like that immediately, did it? The focus seemed to narrow down.
It did. Research shifted towards more specific domains. We got amazing results, don't get me wrong. AI beating chess grandmasters,
Yeah.
expert systems doing specific tasks brilliantly, but they were narrow.
Very skilled, but only in their little box.
Exactly. Then, maybe around the early 2000s, the idea of artificial general intelligence, AGI, started getting more traction again.
A return to that original broader vision.
Kind of, yeah. People like Gertzel and Penichin really pushed the term AGI. Now, defining it is tricky, but for Geekbench, they're using a definition from Francois Chollet. It's basically about the ability to generalize, to learn and act effectively in situations you've never encountered before.
So adaptability is key. Not just knowing lots of stuff, but being able to apply knowledge flexibly.
That's the core of it. And lately, with these huge language models, LLMs, it feels like maybe we're getting closer,
Yeah.
right? They do so many different things, writing, translating, coding.
It seemed very versatile, yeah. Their performance on benchmarks is often really impressive.
No doubt. But here's the rub, and this is central to why Geekbench exists. Are they truly generalizing? Or are they just incredibly good at pattern matching based on the massive amounts of data they've ingested? Is it real reasoning or just sophisticated mimicry?
That's the million-dollar question, isn't it? And Geekbench is trying to get at that. So let's dive into the mechanics. How does it actually generate these new tests on demand?
Okay, so the core is this dynamic process, not a fixed test bank. It makes new games as needed. 3 main steps. First, they use an LLM, specifically OpenAI's O1 in this work, to generate descriptions of new 2-player strategy games. Simple console-style games.
Just the rules in English?
Yeah, natural language descriptions. Step 2, the same LLM, O1, takes that description and writes the actual Python code. It implements the game as a gym environment.
Gym environment, that's like the standard way to set up these interaction simulations for AI, right? Defines the actions, the state changes, how it looks.
Exactly. It builds the playable game, basically, defines the action space, the step function, how to render it, checks for valid moves, all that stuff.
Okay, designs it, codes it. And step 3 was training the opponent.
Right, using reinforcement learning. They use an algorithm called PPO, Proximal Policy Optimization. It's a common RL technique. And they train agents using self-play. The agent just plays against itself over and over to get good.
To create a tough opponent for that specific, newly invented game.
Precisely. So you end up with an agent that's specialized in playing that game well.
Okay, so the whole pipeline is LLM invents game LLM, codes game, -RL trains expert agent for that game. Now, how do they actually test other LLMs?
It's pretty straightforward, conceptually. They take the LLM they want to evaluate, say, GPT-4o or Claude. They give it the game description, show it the current board state, tell it what moves are legal right now.
And the LLM has to pick a move?
Yep, it outputs its chosen move, and its performance is measured simply by its win rate against that specialized RL agent.
That sounds incredibly difficult. It's not just understanding rules, it's strategizing in a totally novel context against a trained opponent.
And the results show just how hard it is. I mean, even top models like GPT-4o, Claude 3.7 Sonnet, they scored really low using standard prompting methods, like only 7 to 9% win rates.
Wow, 7 to 9%. That's surprisingly low for these state-of-the-art models. What does that imply?
Well, it strongly suggests that while they're great at many things, maybe they lack a deeper ability for strategic reasoning or planning in truly unfamiliar territory, even with the rules laid out.
They can follow rules, but maybe not form effective long-term strategies on the fly.
Seems like it. Interestingly, though, other models described as reasoning models, things like DeepSeek R1, O1 itself, and O3 Mini, did quite a bit better. They got win rates more in the 31 to 36% range.
Okay, so models built more explicitly for reasoning or structured thinking seem to have an edge here. That makes sense for strategy games, right? Planning ahead, weighing options.
Absolutely. It points towards the importance of structured decision-making for these kinds of tasks. And the good news is the researchers released everything, the 126 games, the code to generate more, the evaluation setup. It's all out there. Oh, definitely. They had a pretty rigorous filtering pipeline. It wasn't just about generating games. It was about generating good, usable games.
What kinds of things did they filter for?
Several stages. First was keyword filtering. They looked at the descriptions and tried to weed out games that sounded like they'd have ridiculously huge action spaces. Think word games where you could play almost any word computationally, just too much.
Right. Keep it manageable. What else?
Then execution filtering. This was basically debugging. Did the LLM's code actually run? Could you start the game? Did it crash when a random agent played it? Did the visuals work? If the code was buggy, the game was out.
Makes sense. Gotta have working games.
Then timeout filtering. Some games, maybe due to flawed logic, just seem to go on forever, or they crashed a lot during initial tests with a simpler LLM. So games taking too long, over 100 moves or 1.5 hours in these tests, or games that were very error-prone got cut.
Okay, so filter for feasibility, bugs, and excessive length or errors. Was there a final check?
Yes, a crucial one. Establishing an upper bound, they called it. They needed to make sure the games were actually winnable and presented a real challenge. They trained multiple RL agents to different skill levels. For a game to make the cut, a stronger agent had to consistently beat a weaker one, like more than 80% win rate difference.
To ensure there's actually skill involved and it's not just random.
Exactly. And the weaker agent in that pairing became the benchmark opponent that the LLMs would face. If they couldn't find this clear skill difference, the game was considered maybe too random or flawed, and it was removed. That whole process got them down to the final 126.
That's a really thorough vetting process. It really ensures the quality of the final benchmark set. The paper mentions stats on how things like description length and action space size changed after filtering too.
Yeah, it shows the impact. Like the average action space got smaller, meaning they successfully removed those overly complex games.
So what kinds of games actually survived all this? You mentioned 126 diverse games. They used some kind of clustering.
Right. They actually prompted another LLM to look at the game descriptions and suggest categories. Based on that, they grouped the 126 games into 5 broad types: number, board, card, chance, and combat games.
Okay, sounds like a good mix. Can you give us some examples? What's a number game like?
Sure. One example is prime claim. Players take turns picking numbers. Claiming a prime gets you points equal to its value. Claiming a composite number also gets you its value, but you have to give points equal to the sum of its factors to your opponent. Player with most points wins.
Huh. Clever mix of arithmetic and strategy. What about a board game?
There's one called isolation, played on a line of 13 squares. You claim an empty square, but it can't be next to any already claimed square. Goal is to block your opponent so they have no legal moves left.
Needs spatial thinking then. Card game example.
High-low battle. Each player has cards 1 to 9. You play one card face down each round. Higher card gets a point. But here's the twist. If your card was lower than your opponent's card in the previous round, you get 2 points. Adds a memory and bluffing element.
Interesting dynamic. And a chance game.
Digit dilemma. A random 20-digit number is generated. Players take turns taking a digit from either end of the number string and adding it to their score. Player with a higher total sum at the end wins.
Ooh. Deciding whether to take a high digit now or leave it hoping for something better or worse for your opponent. Lastly, combat.
Elemental clash. Players have 10 HP and 4 one-use elemental spell cards. Think rock, paper, scissors, fire beats grass, water beats fire, etc. You play a card, compare elements, deal damage. If you both play the same, you both take damage. First to 0 HP or out of cards loses.
Sounds like resource management and prediction. It's really cool how varied these generated games are. The paper noted number games were most common after filtering, right? Maybe easier to code correctly?
That was their hypothesis, yeah.
Yeah.
Easier to implement, less likely to fail the filtering. Combat games, for instance, dropped off significantly after filtering, probably because the rules and interactions are more complex to get right in code.
That brings up a good point. How reliable was the LLM at translating its own descriptions into code? Did the code actually match the rules?
Good question. They checked this. They manually reviewed 10 randomly chosen games from the final filtered set. And the good news is, in all 10 cases, they found the code implementation was faithful to the natural language description.
That's pretty solid. So the LLM was generally consistent.
Generally, yes.
Here.
They did mention one tiny quirk in a game called Divide and Conquer, where the allowed prime factors seemed to be hard-coded up to 50. It was reflected in the action description, but maybe not super clear in the main rules, so minor things like that might exist, but overall, the coding seemed accurate.
Okay. Let's circle back to how the LLMs performed. We know the reasoning models did better, but why did models like GPT-4o struggle so much? Was it making bad moves or just getting outplayed?
Mostly getting outplayed. The analysis showed very few invalid moves or draws for GPT-4o. It was primarily losing because the RL agent just played better strategically.
So it understood the rules okay, but couldn't formulate a winning strategy over the long haul.
That seems to be the case. It suggests a weakness in long-term planning or evaluating the consequences of moves many steps ahead, especially in these completely novel situations.
Is there an example of that kind of failure?
Yeah, they walk through one trajectory in the paper for a game called Crossover. It involves moving pieces, trying to invade or capture. The LLM, O1 in this case, made a move that looked okay locally, maybe defended something immediate, but it opened up a long-term vulnerability that the RL agent, having trained extensively, was able to exploit several moves later to win.
Ah, the classic short-term gain, long-term pain scenario.
Exactly. It really highlights that potential gap in deep strategic foresight for current LLMs when faced with something genuinely new. It's one thing to follow patterns, another to reason deeply from first principles in a novel, stateful environment.
That's a very revealing aspect of Big Bench. Now, thinking about the future, how does this benchmark scale? Can it keep challenging AI as models get even better?
That's a key strength, actually. They ran an experiment comparing game generation using GPT-4o versus the original O1 model. And surprisingly, far fewer games from GPT-4o, only 10 compared to O1's 126, actually passed all the filtering stages.
Really? Why would the supposedly more advanced model generate fewer usable games?
When they looked closer, they found GPT-4o tended to generate lots of variations on, like tic-tac-toe. Less novelty, less diversity compared to O1's output.
Huh. Maybe it defaulted to simpler known structures.
Perhaps. But the implication is positive for Geekbench. As newer, more capable LLMs come along, you can just rerun the generation pipeline and potentially get even more complex, diverse, and challenging games. The benchmark can evolve alongside the models it's meant to test.
So it shouldn't become obsolete quickly like some static benchmarks can?
Exactly. It has this built-in scalability. They also mentioned maybe down the line, if training the RL agents gets too costly, they could even evaluate LLMs playing directly against each other in these generated games.
An LLM game tournament. Interesting. How does Geekbench fit into the history of using games for AI testing? We mentioned Deep Blue, AlphaZero.
Right. Games have always been a great proving ground. Deep Blue for chess, AlphaZero for Go, Libratus for poker. Those showed mastery of complex existing games. More recently, people have tested LLMs on text adventures or existing game suites, too.
But Geekbench's focus is different.
The key difference is the generated aspect. By creating entirely new games, Geekbench avoids the problem of models maybe having seen the test data or variants of it during training. It tries to ensure genuine novelty.
It sidesteps dataset contamination.
Exactly. It's part of a bigger trend towards scalable synthetic benchmarks like Big Bench or SWE Bench, trying to create evaluations that can keep pace with AI progress and measure generalization more reliably.
And even though LLMs are getting better at reasoning things like chain of thought Geekbench shows, there are still gaps.
It does seem to highlight a continued fragility, especially in these long-horizon, stateful settings where you need consistent planning in a novel environment. The reasoning might be improving, but strategic depth in unknown territory is still a major challenge.
So, wrapping up, what are the big takeaways here? What makes Geekbench significant?
Well, its synthetic nature is key.
Yeah.
It's scalable, you can control the generation process to some extent, and it offers a potentially more robust way to evaluate generalization beyond just pattern matching on known tasks.
It pushes models out of their comfort zone into truly new territory.
Right. Now, it's not perfect, of course. It doesn't measure everything, social intelligence, creativity, and other domains. And the definition of intelligence itself is still debated.
Sure, no single benchmark captures everything.
But Geekbench offers a really valuable and quite unique lens for looking at the domain general capabilities of these models, particularly their ability to strategize and adapt when faced with the genuinely unfamiliar.
Okay, so summarizing our deep dive. Geekbench is this innovative benchmark where LLMs generate novel games, code them, train opponents, and then other LLMs are tested against these specialized opponents.
And the results show it's a tough challenge, revealing potential weaknesses in long-term strategic reasoning, even in top models, while highlighting the better performance of reasoning-focused architectures.
We saw the diversity of games it can create: number, board, card, chance, combat, and the rigorous filtering needed to ensure quality. Plus, its potential to scale keeps it relevant.
It really helps us probe deeper into what we mean by general intelligence in AI and how far current models are from that goal, especially regarding adaptation to true novelty.
So here's something to leave you thinking about. What does it really mean when AI starts creating its own challenges, games that even it finds difficult? What trajectory does that suggest for AI development, and could it lead to types of intelligence that maybe we haven't even conceived of yet?
A fascinating thought. And if you're fascinated and want to dig deeper, remember the Geekbench games, the code, the data, it's all publicly available for anyone to explore. Definitely worth checking out if you're interested in this area.